Hi, so in this today's class, we will see the concept of electric field. Now, suppose if I place a charge capital Q at some origin, say O, and if I take another charge, say small q, and place it at a distance of small r from this charge capital Q, then here, according to the Coulomb's law, both the charges will interact with each other. That is, a charge small q will experience some force on it due to a charge capital Q, while a charge capital Q will experience some force on it due to a charge small q. Now, here to understand the concept of electric field, let me consider any one of the force that is exerted by any one of this charge on the other charge. So, here let me take the force that is experienced by the charge small q due to this charge capital Q. Now, here if I want to know the force that a small charge q will experience due to the charge capital Q, in that case I can easily get it with the help of a Coulomb's law. Now, here if I change the position, say, of small q from r to, say, at a distance of 2r, then here in this case the small q will exert the less force on it due to charge capital Q if you compare it with the previous case. Now, here again if I change the position, say, of small q to at a distance of r by 2 from this charge capital Q, in this case the force that the charge small q will experience will be a maximum, okay, if you compare it with the last two previous cases. Or in general, if I want to show the strength of the force that a charge small q will experience on it due to a charge capital Q, I can show it something like this. Now, when I see this, I can easily say that the force, the strength of the force on the charge small q is inversely proportional to the square of the distance of separation between these two charges. Now, here suppose I take out the charge small q out from the space surrounding this charge capital Q. Now, here the question is, what is left in the space surrounding this charge capital Q? Is there a nothing? Is it an empty space surrounding this charge capital Q? And if there is nothing, then how come the charge small q experiences a force of attraction or a repulsion when you place it in the same space surrounding this charge capital Q? So, to understand this, the early scientists introduced the concept of electric field. And according to this concept of electric field, all the charged bodies produces an electric field everywhere in its surrounding. And here if you bring a small charge, say small q, at any point P in the same space or in the field surrounding this charge capital Q, then this small charge small q will experience a force on it. And this force that charge q experiences is said to be the electric field set up by the charge capital Q. Or in simple words, it is just the space surrounding the charge capital Q in which you will see a small charge experiencing a electrostatic force of interaction with this charge capital Q. So, the space in which this happens, okay, the charge q will experience a force, that space we call it as a electric field. And here the charge that is producing the electric field, that is your capital Q, we call it as a source charge, and a charge small q which is used to test the electric effect produced by the source charge, we call that charge to be our test charge. Now, let us see how to measure the strength of an electric field at any point in a space around a source charge. So, here let us consider a capital Q to be a source charge, and let's take another charge of small q, and let this be a test charge, which will measure the effect of the electric field produced by the source charge in the surrounding space. Now here let r be the distance of separation between these two charges, and here let's consider the medium to be the vacuum. So here let's consider the medium to be in a vacuum. Now I'm interested in getting the strength of the electric field at the point where the test charge is located. So to measure the strength of electric field is nothing but just a ratio of the force between these two charges by the magnitude of the test charge. So I can write it's a force per unit charge. Now here let me put this is my first expression, and here I can write the force here, the F. From the Coulomb's law I can get a force exerted on this test charge by this source charge, and what we write it as F is equal to 1 upon 4 pi epsilon naught into the product of these two charges by the square of the distance of separation between these two charges. Now let this be my second expression, and here if I substitute this equation 2 in equation 1, then I'll get it. If I substitute this, what I'll get is E is equal to F, I'm replacing it by this 1 upon 4 pi epsilon naught Q into Q by R square divided by Q, so which I can write it as 1 upon Q. And here the Q and Q will get cancelled. So what you are left with is the electric field is equal to 1 upon 4 pi epsilon naught into the source charge by the R square. So that's the expression for electric field. Now here the force is a vector quantity. So that means the electric field will also have a direction, so which I can show it like this, and r cap be the unit vector. So that will give the direction of the electric field. So this is the expression to get the strength of the electric field at any position r from the source charge. Now here if you see the definition of an electric charge, we have used a test charge in the definition, but here at the mathematical expression when you see is the independent of a small charge q, which is your test charge. So from this expression I can say that the electric field E is dependent on the magnitude of the charge q. So that's the first point I can make. It depends on the magnitude of charge, or I can say magnitude of the source charge, source charge. Here in this it's a capital Q. And the second thing is that it's inversely proportional to the square of the distance at which you're going to measure the strength of the electric field. So here at a different position, okay, if you try to calculate, this is your source charge. Okay, let me show it here. This is your source charge, and if you try to measure the electric field at a different location, you will get a different electric field here in this case. Now suppose if you measure an electric field at an equal distance, say 5 centimeters or 10 centimeter fixed in all the directions. Here for example you can imagine a hollow sphere, okay, whose center is exactly at the source charge, and the radius of this hollow sphere is of say 10 centimeters, and you are interested in measuring the electric field at a distance of 10 centimeter from the source charge in all the directions. So in this case, you will get the electric strength to be of equal in magnitude for all the locations or on the entire surface of that hollow sphere. Okay, so here the second thing is that this has got a electric field shows a spherical symmetry. I can say it shows a spherical symmetry, or we can call this as our radial fields. Radial field, whose radial field means the magnitude of the electric field will be same, in all the direction if we try to measure at equal distances from the source charge. So that admits. Now here, if I want to get an SI units for this electric field, I can say the SI units. So here, if I see this first expression, I know that it's the electric field here. It's the electric field vector E is nothing but vector F upon Q. Now here we measure the force in terms of Newton. So let me call this as a Newton. And the charge we measure in terms of Coulomb. So which I can say as it will be equal to, SI units will be equal to Newton's Coulomb inverse. I can write it like this. Now here, if I say that if Q, let's suppose consider if Q is equal to 1 in this case, 1 Coulomb, then what I'll get, the electric field in this case, the electric field vector E will be equal to the vector F. Or I can define the electric field that is produced by a charge capital Q. I can define it has the force experienced by a unit positive charge when it is placed at some position. So that is how I can define what a electric field E is. Now here I said while defining an electric field E to be of, this is your unit positive charge. I consider this is my unit positive charge. Now here if you see this, I have shown this is a vector. Electric field is a vector quantity. Now suppose if you have a cases, say the source charge here, let me consider this is my source charge, and if suppose it's a positive Q, and in this case how to show the direction of this electric field, because if I bring a test charge, let me get the same test charge here. So this is my plus Q. I said it's a unit positive charge. Okay. Now when I bring this test charge in a space surrounding this source charge, what I know from Coulomb's law, both the charges will exert a force on this, right? But here where I'm defining the electric field for this plus Q, right? So here the plus Q will exert a force on this test charge, and the force over here will be in this direction, repulsive force, correct? Now that means the force is in this direction, then the electric field over here will be also in this direction, so which will be radially outward. So that's the direction of the electric field. So whenever you see a positively charged, okay, and if you want to show the direction for it, you can show it radially outward. Like that, if you put it the same charge here, in that case you can show it like this. So I can show the electric field for this plus Q to be in radially outward. Like that, if you have a, say, source charge of minus Q, say you are having a minus Q, let this be my source charge, and again here while defining, we are defining in terms of a unit positive charge, and let me take this as my plus Q again. So here, this is a negative charge. That means this will exert a force on this positive charge in inward direction, correct? So that's the force I know. Now, the same sign also goes for the electric field. So here the electric field will be pointing inward. So whenever you see a negatively charged, okay, in that case, the lines, the sign of the direction of the electric field will be pointed inwards. So if you place it a charge over here, a net positive charge, it will be inward and like that. So it's a radially inward. So that's about the direction of the electric field. Now here, this electric field, when you see, this is a force, this is a Coulombian force, right? So both the charges will exert a force on each other. So till now what we have seen is the charge produced by this capital Q. Now while defining this electric field, there is a very important one point, is that if you see this, if you are considering a similar charge on both these bodies, say capital Q and Q, they are of the same in magnitude. In that case, what will happen is that if they are a positive charge, they will repel, and if they are of opposite sign, then they will attract each other. But here, we are interested in measuring the strength of the electric field for capital Q and not for the test charge. This is just a test charge. If you take this test charge to be of some magnitude or which is equal to almost source charge, in that case it will be very difficult to measure the electric field for source charge, because what will happen is that this capital Q will exert a force on this, and this capital Q, this small q will exert a force on this, and a capital Q will also exert a force on it. So they will move, repel or attract. But here, whenever you are interested in measuring the strength of an electric field for any charge, you see that here in a practically, this test charge should be a very negligible, because we are interested in measuring the strength of this, the electric field for this capital Q. So this is just to measure the effect of the electric field. So here I see that this small charge Q is always very small. So the other way of defining this electric field E, you see that the electric field vector E is equal to the limit Q tends to 0, that is very, very small. You consider the magnitude of this small charge to be very small, so that it does not affect this source charge. Okay, see that this Q is not moving away from this small charge. So you see that it's a very small, and then it will be a same vector F upon Q. Now it's again no problem with this equation. If you compare this and this, you will get the same results. It's F by Q. So anyways, the Q and Q is getting cancelled. So you will be getting electric field to be like this. Okay, so only point is that you consider this to be of very small in magnitude, because we are trying to find the strength of the electric field for this source charge. All right, so here that's the equation. Now, a last thing, if I just rearrange this equation 1, I get it the same equation. If I just rearrange this, what I get is vector F is equal to Q times the vector E. So that's the another after rearranging. Now from this equation, what I can say is that even if I don't know the magnitude of the source charge, but if I know the electric field from that source charge, then I can easily calculate the force that any charge will experience when you place it in the field of this source charge. So that's the other way of getting a force on any other charge when it's placed in the space surrounding the source charge. Now let's consider a system consisting of 4 charges. So let this be my charge Q1. Let this be the another charge, say Q2, Q3, and a charge Q4. Now here we are interested in measuring the strength of the electric field at any point in a space due to these 4 charges. So here let me choose a point P somewhere here. So this is the point where I'm going to measure the strength of my electric field due to these charges. So here let me show the position vector from this charge Q1 to this point P, and let this be called as vector R1P. Same way I can show it for the charge 2. So here I can call this as my vector R2P. Same for the charge Q3. I can write it as a vector R3P. And for the 4th charge as a vector R4P. So that's the position vectors of my charges from where I'm going to measure the electric field. So here what we know is that an electric field vector E is equal to the force per unit test charge. So this time let me put it as a Q0. Q0 stands for the test charge. Now here suppose this is a system consisting of 4 charges. Suppose if you're talking about only a 2 charges, say for example let's take a Q1 and some test charge is been placed at this point P, right? So in that case if you take this, what I'll get is 1 upon 4 pi epsilon naught into the Q1 into the test charge divided by the distance of that is R1P square into 1 upon what I'll get is 1 by Q0. Yes. So here the Q0 and Q0 will get cancelled, and what you are left with is vector E is equal to, here I can write the unit vector r cap of 1p. So here I can get the expression as 1 upon 4 pi epsilon naught into the source charge, here in this case it's my Q1, by R1P, that's the square of the distance where we are going to measure the point P, into the r cap of 1p. So that's the first equation I have got for my test charge. So here I write this as my 1p, that is the electric field due to a source charge Q1 at point P. So in the same way I can also calculate the electric field due to a source charge 2 at point P due to 3 and 4. So similarly I can say that, I can say that the electric field due to the second charge at the position P, it will be 1 upon 4 pi epsilon naught into the source charge, here in this case it's a Q2, divided by the distance at which you are going to calculate into the r cap, that's the direction of this, into 2p. So that's for the second charge. In the same way you can get it for your vector E is equal to 3p 1 upon 4 pi epsilon naught into the source charge divided by the distance between them. So that is r cap of 3p. And the last charge, that is my vector E 4p, will be equal to 1 upon 4 pi epsilon naught into Q4 upon R4p square into r cap of 4p. So these are my 4 electric fields due to each of these charges. Now here, when I took this case, the force, Suppose if you are considering a unit test charge is being placed at over here at a point PQ. Now when I see this Q1 and Q0, yes, there is a force, electrostatic force between this. Q0 is going to experience some electrostatic force due to this charge Q1. And the direction, if this Q1 is positive, and in that case, the direction of this force will be like this. And what I know is that the same direction is also available for the electric field. So I can write the direction of the electric field as like this. So this is the direction for my vector 1p. So that's the direction. In the same way, a charge Q2 is exerting a force on Q0 in this direction. So this is a positive charge, then in that case, the direction of the electric field will be like this. So here I can write this as my vector 2p. In the same way, a Q3 will exert force on this, so the direction of the electric field will be in this. I can say vector E3p. And a last charge that will be in this direction. This direction. So here I can say this is my vector E4p. So these are your directions for your electric field at point P. Now here I can make a use of again a principle of superposition, that is adding of all this electric field due to the individual charges at the same point P. So I can make a use of from principle of, I can apply superposition. Okay, I can say that the total electric field at a point P will be equal to just the addition of vector E1p plus vector E2p plus vector E3p plus vector E4p. And here when I add this, what I get is, say, vector EP is equal to 1 upon 4 pi epsilon naught into Q1 upon R1p into R cap of 1p plus, I can say 1 upon 4 pi epsilon naught into Q2 upon R2 of p into R cap of 2p plus 1 upon 4 pi epsilon naught Q3 upon R3p into R cap of 3p, and for the fourth charge it will be 1 upon 4 pi epsilon naught Q4 upon R4p into R cap of 4p. So that's the final answer that you will be getting for 4 charges. Now here, if suppose if you have a n number of systems, n number of charges in the system, then in that case, here what you will get is, I can just say plus dot 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 plus, it will be the addition of the n charge in that P. So for the same expression, if you just consider the n charge, in this case I can say plus dot dot dot, you will be getting 1 upon 4 pi epsilon naught into the Qn charge divided by Rnp into R cap of Np. So once again I can write this, in a more general form as I can say that it's the vector P is equal to, I can take this common term out, that is 1 upon 4 pi epsilon naught, and here I can put a summation here and say I will be running from 1 to the n, and here I can say it's a Qi by Ri into P into R cap of Ip. So that's the more general way of writing this strength of the electric field for a n charges in any system. And here afterwards you can apply a law of parallelogram for these vectors, and then you can get it the net electric field at any point P. So this is the important equation from this session. Now here in this problem, an electron falls through a distance of 1.5 centimeters in a uniform electric field of magnitude 2 into 10 to the power 4 newtons per coulomb, and then the direction of the field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. So here we are told to compute the time of fall in each cases and contrast the situation with that of free fall under gravity. So here we are given two cases. In a case A, we have an electron falling in a uniform electric field of magnitude 2 into 10 to the power 4, and in the case B we have a proton falling. Okay, again the magnitude of your electric field remains the same. Now if you see this, in both the cases we have a uniform electric field with the same magnitude. Alright, so here we are told to calculate the time fall for each of these charged bodies, okay, when they fall at a distance of 1.5 centimeters. So to compute a time fall, we have a equation of motion. So from the equation of motion, I can have the displacement, that is a change in the distance, is equal to u into t plus half into a into t square, where u is your initial velocity, t is the time, and a is your acceleration. Now here if I say that electron started from the rest position, in that case your initial velocity u will be equal to 0. So if I say that if initial velocity u is equal to 0, in that case the distance that I'll be getting is s is equal to half into a t square. And here if I arrange this equation again, what I'll get is a time taken by this electron to cover up a distance of 1.5 centimeter. I'll be getting it as 2 into s by a, yes, and into the square root of this. So that's the time taken by an electron to cover up a distance of 1.5 centimeters, where s is your distance. Here we don't know the quantity a, that is your acceleration. To get the acceleration, I have a Newton's second law. So from, I can say, Newton's second law, I have force is equal to mass into your acceleration. And from this expression, I can get my acceleration as a is equal to f by m. Correct? So that's the another expression. And here, if I substitute this acceleration over here, what I'll get is force by mass. Now, mass of the electron, we know the mass of the electron, it is 9.11 into 10 to the power minus 31 kg. Now here, we don't know this quantity, that is a force on this charged electron, right? Now here, what we know, another expression from today's class, the force is equal to the charge by into the electric field, the magnitude of the electric field. Now here, if I substitute this expression, in this case acceleration, what I'll get, the acceleration to be of acceleration, what I'll get is q into E by your mass of the electron, where q is the charge. And again, if I substitute this acceleration back into this time period expression, what I'll get, if I just substitute this, t is equal to, say, t is equal to square root of twice the s upon acceleration is nothing but qe upon m. So here, what I'll get is q e upon m, so that m I can write it in the numerator part. So that's the final expression what I'll get it to calculate the time fall for both the charged bodies, that is for electron or else same for the proton as well. Alright. Now here in this case, you see the electric field pointing upwards, and this is an electron, okay, in this uniform electric field. So it will experience a downward force. This is having a negative charge and this is your positive charge. So it will experiencing a downward force. Alright, whereas in the case B, you see a proton falling downward. Now in the question, it says that we have reversed the field. Here in this case, the electric field is pointing upward, while in the case B, it's pointing downward. So it's a positively charged, and the field lines, if you see this, they are pointing towards a downward. So this proton will experience a downward force. So now we know here, if I want to calculate a time fall for your electron, in that case, what I can write the time fall, let me say time fall TE. Let me call this as the time fall for your electron will be equal to square root of twice into here the distance that I know, S, into I can say, or here twice the S into the mass of your electron that will come, and the charge what we know is your Q. The charge available with us is 1.6 into 10 to the power minus 19 into you have the electric field. So that's the expression. Now here the distance that is given to us is in a 1.5 centimeters. So first we need to convert this 1.5 centimeters into your meters. So here I can do the conversion. What I can say is that if you are having say 100 centimeters, let me show the conversion. So here 100 centimeters is equal to 1 meters, then 1.5 centimeters is equal to how many meters. So let me put it as a S, and here you can just cross multiply this, and what you will get is 1.5 divided by 100. So that is nothing but your 1.5 into 10 to the power minus 2 meters. So first thing is that you need to convert this distance from centimeters to meters and then put it. And the mass of the electron, we know the mass of the electron, so I can directly substitute it here. So I can start solving. So here I can get it, the time of the electron that you will be getting is square root of 2 into this distance 1.5 into 10 to the power minus 2 meters into the mass of the electron. So that is your 9.11 into 10 to the power minus 31 kg by the charge multiplied by the magnitude of the electric field. So here charge, what we know is the 1.6 into, so here let me say a charge Q is your E times the E. So here E into the E. I'm just taking the magnitude, the charge available on this electron. Okay, so E is nothing but 1.6 into 10 to the power minus 19 into the magnitude of your electric field, that is 2 into 10 to the power to the 4. And here if you just solve this expression, the time fall for your electron will be equal to I can say will be equal to 2.9 into will be equal to 2.9 into 10 to the power minus 9 seconds. So that is the time fall, okay, the time taken by the electron to fall at a distance of 1.5 centimeters. So it's a 2.9 into 10 to the power minus 9 seconds. So that is the time. In the same way, you can also calculate the time taken by the proton. So to calculate the time taken by the proton, so the time taken by the proton, Tp, I can just say it will be square root of twice the S into the mass of the proton by the charge. Q is nothing but your charge, that is E, and I can write it as the magnitude of your electric field. So only thing you're going to change is the mass of this over here. In this case, it's a proton. So what I have is, I can just write 2 into, that's the 1.5 into 10 raised to power minus 2 meters. Mass of the proton is 1.67 into 10 to the power minus 27 kg divided by 1.6 into 10 raised to minus 19 into the magnitude, that is 2 into 10 to the power 4. And again, if you just solve this, okay, you will be getting the time fall for your proton will be equal to 1.3 into 10 to the power minus 7 seconds. So that's the answer that you will be getting. So here we have got the time fall for your electron, and this is the time fall for your protons. Now here, if you see this, the time fall of the proton and the time fall of the electron, here the time that is taken up by your electron is very, very small if you compare it with the time taken by your proton, correct? Now here if you see their masses, the mass, this is the mass of your electron, 9.11 into 10 to the power minus 31, while this is the mass of your proton. When you see their masses, okay, here the mass of the proton is heavier if you compare it with the mass of the electron. So here I can say that the mass of your proton is heavier, I can say, is greater than the mass of the electron. But when you see the time fall for proton and electron, you know, the time fall for the electron, I can say, is less if you compare with the time fall of the proton. So from this, what I can say is that again, it's again the same thing is happening in the free fall under a gravity concept. So from this thing, what I can say is that the time fall of a body is not dependent on the mass. Okay, so here this is electron is a lighter in mass, but the time that it takes to fall down is a bit quicker, I'll say, than compared to the time taken by the proton to fall. So that is the one thing. Now here, if you see this in both the cases, I have ignored the concept of the force of gravity in both the cases. Now, why I have ignored the force due to gravity is that to give the explanation for that, I'll just take this expression for this acceleration. Okay, so here the acceleration, let's try to calculate the acceleration of a proton. So when I say acceleration of a proton is nothing but your charge q times the E by your mass. So let me take the mass of the proton. Now when I calculate the acceleration of a proton, okay, so here the charge, what I know is 1.6 into 10 to the power minus 19 into 2 into 10 to the power 4 by the mass of the proton is 1.66 into 10 to the power minus 27 kg. And when you solve this, what you will get, the answer, the acceleration of a proton is to be 1.9 into 10 to the power 12 meters per second square. So that's the answer that you will be getting for the acceleration of a proton due to this electric field. And now if you compare this acceleration of a proton with the acceleration due to gravity, whose value is g is equal to 9.8 meters per second, right, meters per second square. So here in that case when you compare this acceleration of a proton with the acceleration due to gravity, if you see this, it's a 1.9 into 10 to the power 12, such a big value. So that is the reason why I have ignored, the force of gravity in both cases. And here I have just shown you for the proton, In the same way, you can also get the answer for acceleration of an electron in this electric field. So which will be a much heavier, much larger value than this value, because in the denominator here you will get 9.11 into 10 to the minus 31, which is a smaller compared to this. So the acceleration of an electron will be much greater than the acceleration of a proton. So here the acceleration of an electron will be greater than your acceleration of the proton in the electric field. I can say this is for your when you're placing the charges in the electric field. Okay, and when you compare this with the acceleration due to gravity, these values are very high, so we can ignore this force of gravity in both the cases. So that's the answer for your question. Now here in this question, you are given two charges, Q1 and Q2, which are separated by a distance of 0.1 meters, and here you are told to calculate the electric field at a point A, B and a C. Here the charge Q1 is having a value of, the magnitude of this charge Q1 is 10 to the power minus 8 Coulomb, and for the same, for the charge Q2, it's the 10 to the power minus 8 Coulomb, but it is your negative charge. Okay, so here the magnitude, what I have written is the magnitude. So in the question it is given to be of minus 10 to the power minus 8, which means it's having a negative charge. So I can say a negative. Now let's try to calculate the electric field at the point A, okay, due to these charges Q1 and Q2. So to calculate the electric field, we have an expression. Electric field E is nothing but 1 upon 4 pi epsilon naught into the charge by the square of the distance at which we are going to calculate the electric field. And here 1 upon 4 pi epsilon naught is your small k, and the value for that small k, what we know is the value of that is 9 into 10 to the power 9 approximate value into the charge by, I can say, r square. So this is the expression that I'll be using. So here let's first calculate the electric field at the point A due to the charge Q1. Okay, so I can say the electric field by the charge 1 at a position A is given by 9 into 10 to the power 9 into the charge on this Q1, that is 10 to the power minus 8 Coulomb, divided by the distance at which I'm going to calculate. The distance of separation between these two charges is your 0.1 meters, and A is at the midpoint, so it will become 0.05 meters. So it's just a half of that, so 0.05 meters this square. Now here if you solve this, 10 to the power 9 into 10 to the power minus 8, that will give me a 10, and 9 into 10 divided by this 0.05 the square, that will give me the answer to be of 3.6 into 10 to the power 4 Newton Coulomb inverse. So that's the magnitude what I'll get at the point A. Okay, now here if you see this, what I have calculated is the magnitude of your electric field at the point A. Now this is my positive charge, and for the positive charge, okay, we know that the electric fields will be pointing outwards, radially pointing outwards. So if you are interested in the direction at this point A will be like this in the right side. So the direction is towards the right. So I can show this is the direction of your electric field. So I can show this arrow pointing towards the right. So that is due to this charge Q1. Now we are interested in the net electric field. We have also another charge Q2, that is your negative charge. So let's calculate the electric field due to this negative charge at this point A. So here I can say the electric field by the second charge at this point A will be again 9 into 10 to the power 9 into the charge. Charge available on this Q2 is how much? Negative into 10 to the minus 8. Negative tells you that it's the negative charge, right? The minus sign over here. So let me take only the magnitude part of that. Okay. So here I can say 10 to the power once again minus 8 divided by, and once again the distance of where we are going to calculate remains the same. It's exactly at the midpoint. So 0.05 square. So once again you will be getting the same answer, 3.6 into 10 to the power 4 Newton Coulomb inverse. So we have got a magnitude of the electric field due to this charge, which is both are same. Alright. Now here if you see the direction of this negative charge, the electric field. So this is my negative charge. So here for a negative charge, what we know is that the electric field lines will be pointing inwards. So this is a negative field. So the electric field lines should be pointing inwards. So again, if I want to show the direction of this electric field due to this Q2 will be towards, once again towards the right. Alright, so overall direction, if I just see due to this charge Q1 and Q2, both is having the direction of the electric field is pointing towards the right. Alright, so that's the point. So that is a direction at the point A. Now here we are interested in the net electric field. So they are both the direction of the electric fields due to Q1 and Q2 are pointing in the same direction. So I can add the vectors, right? So here I can, what I do is E1 of A. So I can just add the electric field. The electric field at A is equal to E1 of A plus electric field 2A. So here just the addition of these two equations. So what I have is 3.6. I can say it's the 3.6 into 10 to the power 4 plus 3.6 into 10 to the power 4, and that will give me 3.6 into 3.6, that is give me 7.2 into 10 to the power 4 Newton Coulomb inverse. So that's the final magnitude of your electric field at the point A due to both these charges, and the direction that will be towards the right. So the direction, you can say the direction of this EA. So this is my EA, which will be the direction will be towards the right. Electric field direction towards right. So that's the direction of this. Now we have calculated the point A. So now let's calculate at the point B. So once again we need to calculate the electric field produced by this charge Q1 at a point B, and again by a charge Q2 at this point B. So here, so let's calculate the electric field at your, I can say electric field at the point B due to your first charge. So I can say the electric field produced by the first charge at the B is nothing but 9 into power 10 to the 9 into, once again the 10 to the power minus 8 Coulomb divided by, I am measuring the electric field at point B from this charge. So again the distance that is given to us is same, 0.05. So 0.05 square, and once again I will be getting the same electric field 10 to the power 4 Newton Coulomb inverse. Yes, so that is at a point B due to the charge Q1. So we have this expression. So now let's calculate the electric field. The electric field at due to second charge at position B, that will be again 9 into 10 to the power 9 into the magnitude of the charge 10 to the power minus 8 divided by, the distance, the square of the distance. So here in this case, the distance that will be is 0.05 plus this distance, okay, for the negative charge. So that will be a 0.05 plus 0.05, that will give me 0.1, and this is 0.505. So it will be a 0.15 meters square. All right. Yes. So when you solve this, okay, what you will be getting, the electric field at the position B to the second charge will be your 4 into, I can say 4 into 10 to the power 3 Newton Coulomb inverse. So that's the answer. Now here, if you see the direction, okay, for this electric field, okay, let me first calculate the magnitude. All right. So yes, first let's calculate see the direction of this the charge Q1, electric field due to the charge Q1. So it should be radially pointing outwards for the positive charge. So this is like this. So here the direction at this point B will be towards the left. That is due to this charge Q1. Okay, so this is due to the charge Q1. I can say due to the charge Q1. Now in the same way, the charge Q2, okay, it should be pointing radially inwards, right? So in this direction. So when I just shift this, so here if I want to show the direction, okay, on this at this point B, due to this charge Q2 will be pointing rightwards. So let me use a blue color. So here it will be a pointing rightwards. So this is due to the minus Q2, I can say. So that's the direction. Now here if you see the electric field direction, both are pointing opposite. So when both are opposite, that means they will get cancelled with each other. All right. So here it's a 3.6 into 10 to the power 4. Okay. So which I can write it as, I can write this value as 3.6 into 10, or else I can write this as a 36 into 10 to the power 4 Newton Coulomb inverse. All right, 10 to the power 3. And here the net, if you just calculate the electric field at a B will be equal to the 1B minus the second B, right? It will get cancelled each other. So here I know the value of this E1 of B is 36 into 10 to the power 3 minus 4 into 10 to the power 3. So that will give me a 32 into 10 to the power 3, which I can write it as a 3.2 into 10 to the power 4 Newton Coulomb inverse. So that is the net electric field at a point B. All right. And the direction that will be over here will be the direction due to this charge Q1, because if you see this, the magnitude of this is 36 into 10 to the power 3. All right, and this is 4 into 10 to the power 3. So this is the maximum in magnitude. So the direction that will be at this point B will be the direction due to this charge Q1. So I can say the direction, the electric field direction towards left. So I can say direction towards left. So that's the answer. It will be in a leftwards. So we have done for at the point B. In the same way, we can calculate for the C also. So here for the C, I can say for C, I have the electric field at 1 due to the C is nothing but 9 into 10 to the power 9 into your 10 to the power minus 8 Coulomb by the distance of where we are going to calculate is 0.1 meters square. So at this point. All right. So here when you calculate this, you will be getting the answer to be of 9 into, I can say 9 into 10 to the power 3 Newton Coulomb inverse. Yes. So here the force, the direction of the electric field, it should be pointing outwards. So this is the direction. So I can show the direction in this direction. So that's the pointing outward. All right, so this is my electric field at C due to the 1. So in the same way, the charge Q2 is also, at having a same distance. So I can say that the charge, the magnitude of the electric field due to the second charge at the position C is once again, it's the same value, 0.1. So once again, it will have a same 10 to the power 3 Newton Coulomb inverse. So both are having a same magnitude. So in this case, it should be pointing inward. So that will be the direction along this line. So here I have got, this is my electric field due to the second charge at the position C. So we have got the magnitude. Now here, if you see this, okay, this is my equilateral triangle. So here all the sides are equal and this angle is your 60 degree, right? So that means from here to here, I'll be having my 120 degree. Now here both this magnitude E1 C is equal to E2 C, magnitudes are same. That means if I want to calculate the resultant of this, both the two vectors, okay, I'll get a same value as of this. Why? Because I'm having a expression to calculate the resultant of this two vector is nothing but E1 square, E1 C square plus E2 C square plus twice the E1 into E2 into cos of theta. So here this theta is my 120 degree. Okay, so here I can say this is my E1 C square plus E2 C square plus twice the E1 into E2 and cos of 120 degree. And cos of 120 degree is minus half. So here that I'll get is E1 C square plus twice the E2 C square plus, not plus, that will become minus because cos of 120 is minus half. So minus 2 into E1 into E2 by 2. Okay, so that's 2 gets cancelled. And here from this expression, what I know is E1C is equal to E2C. All right. So here this is my 1C, 2C. Okay. So from expression this, I can get it as E1C square plus E2C square, and using this expression E1C is equal to E2C, what I can write this as my E2C the square. This will get cancelled and what resultant you will be getting is just the E1C. So here when you have both the two vectors, point to make a note is that when you have two vectors, okay, having a same magnitude, then the resultant of that here in this case for theta is equal to 120 degree, we are getting a same result. So the resultant is same. So here I can show the resultant of these two vectors. If I do the shifting of this vector over here, okay, what I'll get is something like this. Okay, that's a law of parallelogram, addition of the vectors, and the resultant, what I'll get it in this direction. So that is the direction. So this is the magnitude and the direction of this electric field at this place. So that is towards a right. So here the net electric field at this point C will be equal to only any one of this value. So that is 9 into 10 to the power 3, and it will be pointing towards a right. So here, so this value that you will be getting is the magnitude of the answer of that is 9 into 10 to the power 3 Newton Coulomb inverse, and it will be towards a right. I can say the direction is towards right. So that's the solution for your problem. So that's the answers. Now what you take home today from this session is that the electric field at any point in space due to a charge configuration is the force experienced by a unit positive test charge placed at any point in that space divided by the magnitude of its charge. And we have an equation to calculate the electric field, which is equal to 1 upon 4 pi epsilon naught times the charge which is producing the electric field in its surrounding divided by the square of the distance at which we are going to measure the strength of the electric field. And here, if this source charge is positive, then the electric field lines are drawn pointing radially outwards, and if the source charge is of negative, then the electric field lines to be drawn pointing radially inwards. So these are the few points that you need to remember from this session. Thank you very much.